So alcohols and alkenes are going to kind of be the tipping point for when we start looking at reactions, and kind of gave you a warning in a much earlier video summarizing organic chemistry, basically saying that you've got to understand a lot of these reactions are reversible, and because of that we have to use shot lids. There's a lot going on. The thing about alcohols and alkenes is that you're going to see a lot of similarities and parallels in the reactions, and for me as an organic chemistry student it made it very hard to understand, okay, why is it this in this case and not this in another case? So the big one here are strong bases. So let's look at two particular strong bases, the hydroxide ion and Tert-butoxide. So both of these are bases. They both raise pH, they both are proton acceptors, and they are both lone pair donors. So they're going to be bases both by the Bronsted-Lowry definition as well as by the Lewis definition. But there are two things that can happen here with these bases. One is we can eliminate the bromine to give us bromide and make an alcohol. The other is that we can abstract this hydrogen and remove the bromide to create an alkene. Which one happens? And the big thing is not which one happens so much as why does it happen. So typically with this OH minus, what we're going to see is a substitution of the bromide. And the reason we're going to see this happen more is that the bromide is small. So if we draw our little bromide beneath it, we'll get rid of the negative. In something resembling an SN2 mechanism, we're going to see the lone pair hit the carbon's going to give up the electrons to the bromine, and we're going to see substitution. Why would we not see this with the Tert-butoxide? Well, the Tert-butoxide here, we have R1 and R2. Our R1 and R2 groups, if they are hydrogen, this is a real possibility that the Tert-butoxide could also do the same thing. So we could get this, and we end up getting an ether in place of a hydroxide. The way we can stop this is if R1 and R2 are CH3 groups, if they're actual carbon chains. So if they are carbon chains and we use the Tert-butoxide, what will happen is our lone pairs will attract the hydrogen. This will cook over to a double bond, and we'll get the electrons back to the bromine to give us a bromide. We'll end up doing an elimination reaction. This big base is the key factor. Big bases prefer to attract hydrogens, not because they don't want to replace the bromine through a nucleophilic attack on the carbon, but because they're just so big, these other R groups are kind of keeping them from doing a substitution reaction with the bromide. So, generally, if we have a small base, something like a hydroxide, we are trying to replace the halogen to give us an OH group. If we have a big base, we're trying to promote a elimination reaction. We're trying to create an alkene. And I'm going to talk about this in another video. We're going to kind of see this with acids and bases as well, to take something like an alcohol and make an alkene. We have to keep track of how big our bases are. Now, the full disclosure for all these videos is to say that you will get mixtures of both. If we use hydroxide, we will get some elimination reaction, but typically we're going to get bromide elimination and substitution with an OH minus. If we use this, we will get some degree of ether. We will get some amount of the Tert-butoxide that does replace the bromine, but because it's so big, most of our product here is going to be the elimination reaction where we generate the alkene. So that's the full disclosure. Again, you're going to see videos with the alcohols and the alkenes that seem to kind of contradict each other. Do this to get this. Well, I thought it was a reverse way with the other mechanism. You're going to have to use the shot liaise and accept that these are not going to be clean syntheses.